All right, we'll get started. So my name is Eric Wolfram. I'm the laboratory manager of Riverbank Acoustical Laboratories in Geneva, Illinois. And I also currently serve as the chair of the ASTM E33 committee, so this presentation is recorded in 2025, and by the end of 2025, I'll be term limited, and so someone else will serve as chair going forward. So first, just a short explanation of what Riverbank Acoustical Laboratories is. We were founded in 1918, so over 100 years ago. The facility and lab operation was funded by this gentleman, George Fabian, and the lab chamber was designed by Wallace Clemens Sabin. We have a whole presentation on that history on our YouTube channel, so if you would like to go deep into our history, check that out. Today, we are accredited by NAVLAP as an ISO 17025 laboratory, and we perform about 26 different testing standards. We average about 1,200 tests per year for over 300 different organizations. So, however, most of our tests are ASTM C423, NRC, ASTM E90, STC, E492, which is IIC, and sound power testing. I also want to quick mention that many of the test standards and classifications that I'll mention throughout this presentation, these are ASTM controlled terms. And what that means is they're defined by a standard which is developed by ASTM International, and specifically the E33 Committee on Building Acoustics, Building and Environmental Acoustics. So this committee meets in person twice a year and has task group meetings, sometimes virtually throughout the year. If you're in the industry or in the business of acoustical testing or products or systems, we recommend participation in this committee, which is open to anyone. And it's a small annual fee, which grants you access to the latest versions of all the E33 committee standards. So just go to astm.org and search for E33. So the main goal today, the main thing I want you to walk away from this presentation with is an understanding of these three kind of basic concepts in building acoustics, what they mean and how they're tested, and what the test results mean relative to your experience of a building. So first, the first term is sound absorption. And when we use this term, sound absorption, we're referring to the ability of a material to reduce reverberation time within a space. Now, don't worry, I'm going to go give you some good examples and deeper explanation on each of these topics. But just to start, remember, sound absorption is referring to the ability of materials to reduce sound reflections and reverberation within a space. Airborne sound insulation, or more specifically, sound transmission loss, is how we describe in building acoustics. It's how we describe the ability of a wall or barrier or window or door, or anything that's intended to block sound from one room through to the other. And then finally, impact sound transmission. And there are different ways this kind of test data can be used, but the standard had in mind when it was developed, and I think is still most frequently used around the issue of footfall noise in multifamily housing or hotels. So the question of how well do I hear someone walking on the floor above? So for each of these general properties of materials, ASTM has classifications. So for sound absorption, the classification that's most commonly used is noise reduction coefficient, or NRC. That's the rating you're most likely to see on things like acoustical ceiling tiles, wall panels, etc. For airborne sound insulation, again, the ability to block sound, you're going to see sound transmission class, or STC ratings. And then third, that reduction of footfall noise condition, you're going to see IIC ratings, or impact insulation class ratings. As you're beginning your journey in acoustics, it is intuitive that all these things might be similar, and that the properties of materials that are good for one must be good for the other, right? And that they're somewhat interchangeable. Very wrong. So they're in some ways often opposite. Different types of materials are sometimes good with NRC and bad with STC, or may have a good STC but a poor IIC. This is common all over the place. So there is, from a physics point of view, there is some overlap, but it's really better to think of these as three completely isolated properties, three ratings which have nothing to do with each other. And if your question is in regards to STC, then NRC does not answer your question. So our lab, and labs in general, are built to control all sorts of properties and paths that sound might take to be able to identify these three classifications for a specific material. So this rendering you see here, this was a rendering from the 1920s, early in the lab's history. It's really cool. It shows like how the main chamber was isolated, the massive walls, room within a room design, and to control outside noise from penetrating into the chamber. And then the design of the room in terms of its length, width, and height were intended to be conducive to creating a good diffuse sound field. And today we also control temperature and humidity and various other factors to make them constant, so that whenever we run tests, we have the same environmental conditions. All right, so the first property that we'll look at in depth is sound absorption. And remember, this is a property of materials, or property related to interior of space. So it's the main consideration with sound absorption is reverberation. So one could think of, the sound absorption performance of a material as its ability to reduce reverberation. So what is reverberation? Well, within an enclosed space, hard surfaces will tend to reflect sound waves. Now this diagram on the right here, this kind of gives like a simplified explanation of what's happening with a sound reflection. Now generally, sound waves reflect off of a surface where the angle of incidence equals the angle of reflection. So they have sort of a predictable reflection pattern similar to, let's say, like a billiard ball, right? However, in reality, and we often in acoustics create these demonstrations with kind of focused sound waves coming out almost like a laser towards the wall, or a single line towards the wall. The reality is that sound waves are incredibly messy. And not only is the speaker creating sound level at different positions around the speaker, which is all coming out in different directions, but those waves, as they propagate towards the wall, are constantly dispersing. So the sound is sort of flowing in all directions. So as all these sound waves are flowing towards the wall and reflecting in all directions, it creates this echo, right? This reverberation within the space. We measure that in terms of the reverberation time, which is generally the time it takes that sound field to decay 60 decibels after the source is interrupted. So I'm going to give you a couple examples here of different spaces or sounds recorded in different spaces and how the room itself affects the sound. So believe it or not, in these first impulse sounds, this is the exact same device, the exact same noise source, recorded from the exact same distance, from the same microphone at the same level. The only thing that's changed is the room that this recording is made in. So this first recording will be of an impulsive sound in an anechoic or dead, we call it dead environment. Actually, that's not really an acoustics term, that's like an audio guy term, audio person term. So I'll play it a couple times for you because it's real quick. So listen, you hear the metallic clarity and detail of this object. This is actually a 1950s pop gun that some of you have seen in our lab. And you hear like the very clear detail of the mechanism. All right, now we'll go to, again, same distance, same object, just only thing that's different is the room it's recorded in. So you hear, you lost all the detail of the mechanism, and you hear this long reverberant tail. This is, the recording was made in our room 0, our main diffuse field chamber. So this reverberation was very important to a space, especially like a critical listening space, but really any space where humans are occupying and talking and existing in. So in most cases, reverberation is like a type of noise. It's detrimental to the purpose of the space. Now I have to be careful because there are some very important counter examples to that, and which some of the acousticians are already shuffling in their seats saying, no, it's not. Okay, so something like a concert hall, especially a concert hall that is intended for choral music or orchestra, having a well-balanced reverberant sound field is very important to the musician performance and the experience of the listeners in that space. It's part of the experience. It's important. Even then, there's a limit, like not unlimited reverberation, and even this 6-second example is too long, but you know, a good, well-balanced reverberation tail. Probably the upper end of the, you know, if there's a spectrum of things that want reverberation versus don't want reverberation, I would say on one end of the spectrum would be pipe organ music from like a cathedral or a classical worship space, and like Gregorian chant. Those would love a lot of reverberation. Now on the other end of the spectrum would be something like a movie theater, you know, where you don't want this echo, and this echo would interfere with the purpose and function of that space. I'll give you a good example. So this here is some speech recorded in a dead environment.
In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapidly moving articulation, either of speech or music, should be clear and distinct, free from each other and from extraneous noises. These three are the necessary, as they are the entirely sufficient, conditions for good hearing.
Now, same sound source, same distance, only thing that's changed is the room.
In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapidly moving articulation, either of speech or music.
So, in fact, I'm realizing I should have played it the other way around, because you have a clue. You already knew what the word said, but if you didn't know what the word said there, you'd have a real hard time making out speech. So that reverberation it's detrimental to your ability to understand speech in that environment. And all right, so the field of acoustics, or building acoustics, started with this equation right here. This is the Wallace-Sabin equation. And this was developed by a gentleman named Wallace Sabin, and he was a professor at Harvard that derived this equation and basically started the whole field of architectural acoustics. It's a very simple equation, which allowed us to allowed people at the time to predict reverberation time. And actually, this equation is still used today. It has its place and purpose in the field of acoustics today, although there are other alternative equations for other types of environments, and there are sophisticated acoustical modeling programs which will allow you to do more with more detail. However, the validity of this equation still holds. So basically, we're able to predict the reverberation time of a space knowing the air volume and the total sabins present in a room. Sabins is the unit of sound absorption. But what is a sabin? We have different ways of explaining this, and like a lot of physics metaphors, they can be very helpful, but also have their limits. And at the very high end of understanding, the metaphor is actually counter to understanding. So we'll try our best here. So I think that Wallace himself, and at least very early on, the explanation of a sabin was that one sabin was like 1 square foot of open window. What we mean by that, if you look at this image on the right, light is reflecting off the surface of much of the concrete wall, except for these areas here. In those areas, all of the light is absorbed and none of it is reflecting back. So in this metaphor, one sabin is like 1 square foot of this open window where no light is reflecting, but for sound, so where no sound is reflecting. Truly, it's really defined by this equation, but I think this is a really good understanding, and it's very commonly used today. This Wallace-Sabin equation is the basis for the ASTM C423 test method. So a variation of this equation, which is solved for the total sabins, and with a adjustment to correct for the speed of sound in that chamber, is used. So how we run this test is we will test the reverberation time in the empty space, and then we will install the material under test and then measure the reverberation times again. Using this equation, we're able to determine the total sabins of absorption in the empty chamber and the total sabins of absorption in the chamber when the material is installed. If you subtract the empty chamber, then you're left with a quantity of sabins attributed just to the sample under test. So a sound absorption area that has been added to the chamber just from adding this device or object or whatever it is under test. If the sample under test is a flat 2-dimensional material, then we can determine the sabins per square feet of that material. So in this example, we have an 8-foot by 9-foot rectangular patch of material, which is 72 square feet. So if we measured 72 sabins of sound absorption, and we have 72 square feet of material, then we would have 1 sabin per square foot. In architectural acoustics, we call that a sound absorption coefficient, so 1.0. Now, that term is not technically correct. It is not actually an energy absorption coefficient. However, that's the way, we have used that term in this industry. It's very traditional. So sound absorption coefficient. And for the most part, 1.0 is seen as 100% absorptive, but really what it means is you have 1 sabin per square foot. Now, if you have a sound absorption coefficient of 0.5, that's sometimes seen as being a 50% absorption, which is approximately correct. Where it breaks down is it is possible to achieve, it's actually possible and common to achieve rates of absorption greater than 1 Savin per square foot. So greater absorption coefficients greater than 1.0. And this is not alarming or anything like that. It's just the nature of the test. And maybe someday we'll do a presentation just on that subject. But yes, it's possible to have absorption coefficient greater than 1. So what is NRC? NRC is the classification or the single number rating for a test with a variable performance across different frequencies. So what that means is, this is an example of a test result for a sound absorption material. This is actually pretty good representation of, let's say, a 2-inch thick sound absorption core, something like that, just generally. And you see the performance is very different at different frequencies. So above 300 hertz, you're above 1.0 for most of the range above 300 hertz, but then the performance drops at lower frequencies. So it's harder to absorb lower frequencies generally. This is sort of complicated, right? And if you're marketing acoustical materials, you don't want to have to explain, well, our material has 0.45 at 160 hertz and 1.1 at 1,000 hertz. You just want a single number that can be used in a broad way to compare material A to material B. So the traditional or historic rating for that single number was the noise reduction coefficient, or NRC. The definition of NRC is it is the average of the sound absorption coefficients at 250, 500, 1,000, and 2,000 hertz, rounded to the nearest 0.05. Now, some of you technical people may have some questions. Yes, so there are a number of problems with this, and this is not the way the industry would do things if it was to create a number today, a single number rating today. We have to remember this goes back to pre-computers, where everything had to be calculated by hand, and just a different understanding of when to round and how. Today, more recently, they developed a sound absorption average, or SAA. This takes a range of all the 1/3 octave bands from 200 to 2,500 and rounds to the nearest 0.01. At ASTM, we believe this is more technically correct, and it's also the currently defined single number rating. However, most of the industry still references NRC ratings pretty broadly. So our reports give both. So what are the properties of material that contribute to sound absorption performance? Most sound absorption materials are porous or fibrous media. So that porosity and fibrous material is very important. So as sound flows through it, energy is lost as it moves through all that material, is lost in the pockets and all the different transfers of air to material to air. Thickness is very important for this type of absorber. So it takes about 2 inches of porous fibrous material of sufficient density to get an NRC of 1.0 with no airspace behind it. Density does matter, maybe less so than thickness, but density is important, and too much density can actually start to reduce performance as well. So there's a sweet spot, somewhere in the 5 to 8 or 9 pounds per cubic feet where materials are very effective. If you'll often notice that some materials are installed with a deep airspace behind them. For example, acoustical ceiling tile. That airspace is a way to cheat, basically, in a good way, and get more performance out of a material than it should be allowed based on its thickness. And this is allowed. You are allowed to test with an airspace if the material is typically installed with an airspace. So for example, acoustical ceiling tiles, and there are a number of different mounting methods which define different types of airspaces, but they have a very significant impact on the performance of the material, and therefore the results are really specific to that mounting. The surface is very critical. that surface needs to be air permeable so that the sound waves flow through the surface and are absorbed by the core. Yes, so painting the surface of an acoustical wall panel, especially a very thick latex paint, multiple coats with a big woolen roller, yes, regardless of what anyone tells you, that will reduce the effective NRC rating. There are products out there that are tinted and painted by the manufacturer, and those companies put a lot of engineering into making that surface work well, so that when they test it, it is painted and coated and achieves the exact NRC. That's actually a difficult engineering problem for acoustical product manufacturers to get that just right. There's another category we won't go into too much, which would be like Tune's diaphragm absorbers. So it is possible to make a sound absorber that has a resonance. Typically, these are effective at certain frequencies, though, and not broadband. So if you think back to the I don't know, you'd probably say this is 1980s, but I remember this as a 1990s office space, right? You have the acoustical ceiling tile and the carpeted floor and the cubicle partitions. And you know, Hollywood made a lot of movies and TV shows kind of disparaging this office space environment and how it was so terrible for workers, right? Well, there was one area where this space worked really, really well, and that was acoustics. So if you think about it, the entire ceiling is sound absorptive. So if this was a 0.85 NRC ceiling tile, that's 0.85 Sabins per square foot. You have a lot of square feet of sound absorbing material here. So a lot of Sabins in that room. Even the carpet at high frequencies was absorptive, and these cubicle partitions actually did a decent job of absorbing reverberation within the space. And any sound that went up over the top of the partition, some diffracted around, but there was no reflective support off the ceiling. So you had more isolation in your cubicle. You had less distraction and a more focused type of environment. Now, the space on the right, this is architects listened, and they heard, you know, the critique of that office space in the cubicles, and everybody hated cubicles, right? So they came up with the open plan office. And you'll notice some things here. This is a very beautiful space, but the hard surface floor, that concrete floor, all of the glass, that hard, high elevated ceiling, and no partitions, there is literally no sound absorption at all in this photo. Well, maybe these chairs, depending on what that material is, a small amount from the chairs. So the space on the right is going to sound more like that reverb chamber demonstration and less like that anechoic or dead space situation. So it contributes to distraction and unpleasant environment. And my opinion, around 2010s, in the 2010s, when every office was converting to this, there's maybe a reason why everyone was so excited to finally go work from home to escape these reverb chambers. So that's sound absorption. Next up, sound transmission loss. This is, again, referring to the ability of walls to block sound. Sound transmission loss measures how well a wall will prevent you from hearing your neighbor through that wall in a condominium. So airborne sounds, human voice, television, a dog barking, these sorts of things we would consider airborne sound. So what are the properties of a material that generally give higher sound transmission loss or a better ability to block airborne sounds? Most fundamentally is mass. So generally, in almost all very broadly, heavier is generally better. So heavier materials are more massive, and therefore it takes more energy to make them move or to make them vibrate. Limpness, so this one's often counterintuitive, and we'll hit on this in a couple of different ways. but stiffness works against you generally for sound transmission loss. So stiffness is not your friend for sound transmission loss generally. This photo in the bottom right is a material that's been in our lab for decades. This is lead. And if you think about it, lead is kind of a classic, legendary material used in recording studios from the mid-century on, creating sound isolation. And lead, what does lead have? It's very massive, very heavy, and it's also very limp. So it was sort of a perfect ideal material. Now, for various reasons, people work with lead much less than they did, in the 1950s. So further, air tightness, small gaps will kill your STC performance much more than you might think. And a good example I give of this is, so you're in your car, you're driving in your car on the highway. If you open your window all the way open, you hear all the air turbulence noise and tire noise and everyone's engine and everything just coming clear through the window, right? If you close that window halfway, it sounds almost the same, right? 3/4, okay, now you may have noticed some change, but it's still very loud. 7/8, still very loud. It is only when the window fully seals into the top of the door, into the seal, where you get that kind of almost airtight seal, that's when the sound sucks away and is gone, right? So you had to achieve that airtightness in the window to achieve the maximum possible STC out of that window. Next up, damping. This is important. This is a critical factor of how the wall is performing. It's not always thought of in as much detail as the others, but this is basically friction in the vibrating system, whatever it is. So basically dissipating energy in that vibrating system. And then finally, cavity absorption. So if you think of this acoustic guitar, the effect of that wood body on the guitar when the string is played is that it kind of amplifies, or it resonates in a way that brings that energy, enhances the sound, right? You don't want that. You do want that with a guitar, but you don't want that with a wall assembly. So imagine if you stuffed the body of that acoustic guitar with fiberglass or mineral fiber insulation, then played it, it would be totally dead. You probably barely hear the strings, right? So that's basically what absorption does within a wall cavity. It reduces the resonance of that hollow cavity in the wall. So it's very important to note that STC is a system performance and not a material performance. What we mean is you don't have an STC rating for each of the components of a wall. You have an STC rating for the sum total of the wall or the window or any other acoustic system. So a good example, this is from a slide I gave to a drywall installers trade association. I was like, oh, this is a really good example. So when you're thinking about systems or wall systems or doors or windows for sound transmission loss for STC, you want your system to be more like the 1970s Cadillac, which was heavy, floating, and airtight. So the isolated suspension keeps the vibration of the road out of the body of the vehicle, soft floating suspension, and a really massive vehicle that took a lot of energy to make move. And then airtight and closed cabin, which kind of blocked out the outside world, right? So that's the way you want to think for wall assembly. You want your wall assembly to be more like the Cadillac and not like the go-kart, right? The go-kart is very, very light, very stiff, and open. So what does this mean for the wall assembly? Generally, more layers is better. Adding mass of the gypsum board will improve generally up to a point the performance of the wall assembly. And there are certain materials that are made to be lightweight. Consider that that lightweight alternative may affect your STC rating. Stiffness is, again, very critical as well. So, and sometimes counterintuitive. So lighter or thinner steel is actually better for STC. So think of it as the steel is lighter, it's more flexible, and the very light gauge steel is almost like a resilient. It's, if you hold it, you can almost crush it in your hand. It's very resilient on the very light gauge steel. And then on the other end of the spectrum, maybe let's say like a 2x4 wood stud is very, very rigid, right? Very stiff. So the same gypsum board on both sides, the same insulation in the cavity, and the same spacing and fasteners, you could, or I should say, tighter spacing and tighter screw pattern could range from STC 50 on a single layer gypsum board wall with really favorable framing conditions, down to STC 36, 37 on the same gypsum board, the same materials, but more rigid framing. So again, wider stud spacing is generally better for STC. So like 24 inches on center will generally perform better than 16 inches on center. And then a wider fastener spacing will generally perform better for STC. So tighter screws pattern, you know, the contractor may think they're doing an extra good job because the wall is really important. We're going to put a lot more screws in. That actually can hurt your STC very significantly sometimes. So now some of you are already thinking, okay, this is a problem because all the things we just mentioned are not possible in my building because we need that wall to be structural and we need it to pass fire requirements. Well, the good news is that when your wall needs to be stiff for those reasons, there are other alternative products that are able to reintroduce that flexibility underneath the gypsum board. And that's where like resilient channel or isolation clips come up. So again, a single layer 5/8 type X gypsum board on both sides of a stud wall with the same insulation in the cavity, that could range from STC 37 to STC 50, just depending on these factors. So, and then finally, air tightness. In the lab, we will caulk the track to the test frame so that there's no path of leakage around the test frame. And then after the gypsum board is installed, we isolate the gypsum board a small amount from the test frame, and then we fill that with a flexible airtight mastic seal all the way around both sides. So in the lab tests, we intend to eliminate that flanking around the sample or through the test apparatus so that the sample can perform at its best. But in the field, you want to consider that as well. And then finally, cavity absorption. We want to make sure that this is not a hollow cavity that will resonate. I have to be careful how I say this one, but you know, the properties we talked about with sound absorbing materials apply in this cavity here. And you want to avoid materials that are very, very rigid to the point where they're increasing the stiffness of this wall and not adding much mass. So think about that. So materials that might be stiffening the wall and not adding much mass, those could actually hurt your STC rating. So, and then finally, damping. There's a way to introduce more friction in the vibration of these materials. So this would be something like the viscoelastic damping compounds or the quiet gypsum board products that are out there. These are real materials. They have real benefits. They're a good tool in the toolbox. But again, remember that you're looking for systems performance and not just one magic bullet material that might perform in all possible conditions. So I'll tell you a little bit about how we run this test. We have a special set of chambers that's built where we have two reverberation chambers that are joined by an aperture. In this case, room 1 might serve as our source room. So we're generating about 110 decibels, 120 decibels of pink noise in that room. I mean, imagine that you're standing at the bottom of Niagara Falls inside of a cathedral. That's what it sounds like in that chamber. You don't want to be in there. And then we measure this average sound level, spatial and time average in that chamber. And then we make that another measurement on the other side of that chamber. And then we correct for the area of the sample and the presence of sound absorption in the receive room. There's also an ambient noise correction, but that's in a lab condition, that's almost negligible. So that process tells us that all the sound that we're measuring in this receive room is coming through the sample because we've isolated all other paths that sound could take around it. And the sound level, the reduction through that sample of that size is determined there using this equation here. So the transmission loss is the source level minus the receive level with that correction I mentioned before for area and sound absorption. Here's a photo of our test environment. So this would be chamber 1 through the aperture, and then chamber 2 we're looking at. So most wall assemblies will be built in this 8-foot wide by 9-foot tall aperture. You know, most low, medium performance systems, it's favorable to test them at this size for efficiency. Here's some photos of a typical like wood stud framing installation. Insulation going in steel stud assembly, and then gypsum board installed. Now you see the perimeter of the wall. We always seal that with mastic. Obviously you wouldn't do that in the field, but you do want to make sure you get an airtight seal around the perimeter in your field condition as well. In the lab, almost all tests are run with foil tape and acoustical sealant, sealing the joints. And this was proven in a paper by National Research Council of Canada to perform the same as a level 3 joint compound treatment, which is good news for the labs, because if we had to do a level 3 joint compound, it would take multiple days to do a single test, versus with this method, we can run multiple tests in a single day. And there's no difference in the STC rating. So similar to when we discussed NRC, STC has a similar but different kind of classification to it. So a way to take, in this example, a complicated sound transmission loss spectrum and turn it into a single number for the purposes of comparison. So in this diagram on the right, the red line is our actual sound transmission loss performance for a wall assembly. And you'll notice that, you know, the performance is weaker at lower frequencies and generally better at higher frequencies. This is very typical. It's why you know, when you hear someone with a loud car stereo, you hear the bass, but not, maybe you can't understand the clarity of the vocals or the cymbals, that sort of thing through the car. It's because the low frequency waves transfer very efficiently through most materials. This is also why nobody should run a subwoofer in a multifamily housing situation, because even with this wall here, which barely passes building code requirements, at 80 hertz or 60 hertz, which a subwoofer could produce, you have very low transmission loss, which means that subwoofer is almost as loud for the person in the next room as it is for the person in the room listening to it. So anyways, back to STC rating. So we have this complicated curve, and we take the standard reference curve and we fit it to the actual test results. This is done through a very simple procedure where you increase it until you have a maximum of 32 deficiencies. A deficiency is a point where the red line is below the blue line. You see we have deficiencies here and here. So you have a maximum of 32 deficiencies overall, and or not more than 8 deficiencies at any 1/3 octave band. So this 8-point rule will overrule. So you're not allowed to have more than 8 deficiencies at any band. Then the STC rating is the value of that curve at 500 hertz after it has been fit. So you see here, you have STC 50. So one thing to note with STC ratings is there is a very wide range of wall performance contours that could all fit to the same STC ratings. So depending on your situation, you may, like acousticians will often want to see this 1/3 octave spectrum. You know, if, for example, let's say you have, you're building a wall that's a partition to block out sound, and you know that your noise source is very strong at 2000 hertz, then this wall is maybe not the one you want to build because it's weak at that single band, and that weakness at that band is not really revealed in the STC rating. All right, finally, impact sound transmission. Now I have to tell you, this is probably the most, this topic is, I've seen more grown men crying in my life about anything, about this topic than about anything else. So imagine that you bought your dream condominium. You spent $2 million on this condominium, and you move in, and very quickly realize that you hear every single footstep, tap, 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 back and forth all day long in the ceiling above. You hear every footstep from the person walking above you all day long. Now, acoustics sometimes seems like it's not that big of a deal, or less important than, let's say, having the right kitchen cabinets and countertop. But when you have that situation and you're very noise sensitive, you don't care what your countertops were made of. That is the #1 problem in your entire life, and there are really no easy solutions here. So we encourage, whenever possible, that this consideration is made when a building is built and/or when floor coverings are being installed, so that that you do it right the first time. So how do we test this? So in the very early days, I think like 1950s, let's say, the method would be they would have a woman in high heel shoes walk in a figure-8 pattern on the floor and make measurements below that, and try to standardize the gait and the speed and all that stuff. So this is problematic for a lot of reasons, right? So they came up with this machine. This is a standard tapping machine, and this is what we use in our IIC and field tests, our AIIC tests in the field, so E492 and E107. So this machine has a series of metal hammers, which are all dropped from a defined height, and this sequence happens at a defined speed. And it's basically like almost like an inline 5 engine. It's constantly tapping on the floor, and it's loud, but it creates this kind of controlled standard impact noise function into the floor assembly. We'll take that machine and place it on the top of a floor ceiling assembly, and then we make measurements in the room below. So the source room and receive room is below. There's also, similar to E90, there's corrections for the sound absorption and ambient noise in the receive room. This is a photo of our floor ceiling test aperture. So you see there's a chamber below and then a chamber above. We can build almost any type of floor ceiling assembly or roof assembly in this aperture. and test it both for airborne and impact sound transmission, so STC and IIC. The tapping machine is placed in a series of positions on that floor after it's been installed. So what are the properties of materials that will contribute to its impact sound isolation or its IIC rating? So maybe, in my opinion, one of the most critical factors is that flexibility on the surface. So if you go back to, the 70s and 80s in multifamily housing, you almost always had carpeted floors in apartments. And this is why it was not as much of a hot topic back then, because that carpeting does a really good job of preventing the footfall noise from getting into the structure, into the subfloor structure. It eliminates that strike at the first possible position. So that surface is very critical. However, we know that the modern homeowner, modern consumer would rather saw off their own arm than have a carpeted living room, right? I get it. So the hard surface flooring options like tile and wood and laminate, they just are inherently worse for IIC performance. And so you want to take special consideration on isolating these floors. Again, generally, it's better if you can get that isolation to happen further up in the structure. This is an example here, courtesy of Maxon, of Acoustimat that might be isolation. And then this image here, right, courtesy of Kinetics. If you can't isolate at the surface, there's an option to be able to isolate at the ceiling below. And there are some circumstances where you are kind of forced to do that. So they have an isolation spring system that will isolate that gypsum board from the building structure. So also mass is also critical, and the presence of generally a suspended ceiling in general is also very important. That's another trend, as the demand for higher ceilings in condominiums is counter to the interest of the acoustics. So exposed slab configurations where you look up from the room below and you see the actual concrete subfloor without anything suspended, that's important to take consideration in acoustic performance there, because the ceiling can help you quite a bit. So as we mentioned before, the IIC rating, and this is really critical to hammer in on IIC performance. IIC is not a materials rating. IIC is not a rating on an underlayment or a floor covering. IIC is a rating on the entire subfloor, of which that floor covering or underlayment is one component. So you have you will sometimes see, maybe if you go into the big box store, you might see an underlayment with a label on it that says IIC 74, let's say. So the question one should ask is, well, okay, what was the assembly that was tested? Because this IIC 74 doesn't tell me anything. In fact, it's a clue that it was probably a pretty substantial assembly. So you'll want to look at the laboratory test report, which will give you specifications for exactly what was tested, including the finished floor, underlayment, subfloor, suspended ceiling, any isolators that were in place, insulation in the cavity, basically the whole buildup. This is very important. So, like I said, with floor ceiling assemblies, especially, you really want a lab test report to verify that before you pay to have a flooring installed or you build a building, that you know that you're going to have a satisfactory performance. So, as an example, this is our 6-inch concrete reference slab. We do a lot of different tests on a lot of different floor, finished floors, underlayments, suspended ceiling systems. The base slab by itself gets a STC 56, which is good news, right? So that tells you, you pass the minimum building code. We'll get to that in a minute on what that is. But you pass that with just the slab. That's because even though the slab is very stiff, there is a lot of mass here. So, and that is really doing the work on the airborne sound transmission. However, even though you get STC for free, IIC is a big consideration. So without any consideration, without any floor covering, you would have an IIC of 27. So if you had a polished concrete floor and an exposed slab on the room below, that's a very poor IIC performance, 27. So what do you want to look for? Like I mentioned, you want to ask for an acoustical lab test report. And lab test report, it's usually not a 1-page or 2-page document. It has a number of things. So I'll quickly go through what to look for in a lab test report. So obviously the testing agency, who performed the test, how are they qualified to perform the test? So in our case, we're accredited by NAVLAP, which is the US federal government's accreditation agency. There are other accreditations as well, but you want to make sure that that this is a lab that's accredited to perform as a lab as well as to perform this test. We'll mention in this first paragraph here what the standards were that were followed to perform the test. We will tell you when the test was performed. The information provided by sponsors section. So starting with 2017, the 2017 version of ISO 17025, they required labs to separate information that's provided by the sponsor versus information that's directly observed by the lab, which is really smart. So we have a section for sponsor provided information, as well as a section for our own observations. And then most of our modern test reports starting around 2012 and later will have photos of the sample. And I don't know about you, but for me, it's a lot easier to figure out what's going on in a build by looking at photos than reading paragraphs. So we'll also provide 1/3 octave band results, the single number rating, and you'll also have a certified signature on every report. So once you authenticate this signature once, I believe that anytime you see a future report from me, IdenTrust will validate that signature when you open the PDF. So these ratings, the airborne and impact sound rating, STC and IIC, are referenced in the International Building Code for multifamily housing. So for airborne sound insulation, they want not less than STC 50, or if it's field tested, not less than NNIC 45, which is the field test, sort of not equivalent, but the field test version of E90, which is E336. Now, one might think, well, we should try to just do the field test because that's easier to pass than the lab test. Actually, that's not true. Oftentimes, a field test can be more challenging because there's a lot of factors that you can't control that could be influencing the test results. And we are seeing more and more where developers are being asked to provide both the lab test prior to construction and then the field test validation afterwards. So, and then impact sound insulation, IIC 50, and similarly, they allow 5 points flexibility for the NISR, which is the field alternative. So it should be noted that these ratings, STC 50 and IIC 50, even though this is the building code requirement, this should really be seen as a minimum acceptable performance for multifamily housing. So this is not soundproof, this is not high quality, this is, we did the minimum and we got STC 50. Luxury, might be in the range of STC 65, 60 if you can, or 60, 65 if you can get it. And then 55 to 60 might be a good, reasonable target for, high quality condominium. So, but there are a lot of different considerations there and a lot that goes into designing for that. So in our experience, most of the time when there are really significant complaints, it's around this level or slightly lower. You know, oftentimes the worst case scenario is someone, you know, does a field test and they get NNIC 45 and they're not happy with it, but it passes the building code and that's that. So just a consideration. So anyone that's designing buildings to try to shoot for higher than these. And where can you find information on these test reports? I'm going to share a couple examples for you that I really like. Probably in my experience, like one of the best comprehensive directories of wall assemblies and floors is this USG Design Studio. They give fire ratings and STC ratings for all different types of assemblies, and I really like this layout. There's also the GA600, which provides a big list of acoustical and fire performance for different systems. And then products manufacturers will often make our test reports available on their website. And you know, if you see numbers and you're being held accountable for the acoustic performance of the building, I recommend reaching out to the technical support of the manufacturer and ask them, you know, for that test report. Clark Dietrich is another one. I really like the way they lay out their test results and for all their different products and systems. We also perform field testing as well, but you notice in these pictures, you know, in the lab, we have perfect conditions. We control for all variables and eliminate flanking paths, but then field environments, as you see here, are often not ideal. So like I said, field testing is an important tool, but it's part of the factor. So the photo here on the right demonstrates, this came from one of our customers, noise barriers, and they saw that like they put in very high performing door system, but when they got to the site, there was a big open gap where the wall met the ceiling, which was causing a flanking path around the door. So it didn't matter how well the door performed. The actual sound insulation between the two rooms was limited by this gap here. So in field tests, you're not really measuring just the intended path of sound through the intended wall, but all possible paths that sound is taking from the source room to the receive room. So when to do lab tests versus field? So lab tests are performed on products and systems before the sale and installation, and field tests are performed on building systems after the building is built. So one thing to remember, whenever you hear these ratings, STC, NRC, IIC, these are all lab test results. So these are not field tests. There are field tests that are similar, but they have different classifications. So an acoustic requirement for an STC rating is asking you for a lab test, and that typically is sponsored by the product manufacturer, although we're seeing more and more, you know, mock-ups for a specific building, project-specific mock-ups. So when you're involved in the construction of a building, you know, the acoustical considerations are very important, and we talked about, you know, where things can go sideways and all that complexity, and then balancing that out with the structural and fire requirements, which even us acousticians will say, yeah, fire is directly a life safety issue. You should not compromise your fire performance. So that's one of the things that an acoustical consultant will do on your project is help to work with those various trades to ensure a good outcome. So there's a trade organization for acoustical consultants, the NCAC, and they have a directory, and you can most likely find someone in your area that's qualified to consult on the project. Another credential that I think this might be the most well-respected credential in the trade of acoustical consultants or acoustical engineering. This would be the INCE board certification. And there's a directory on IIC USA website, which can find board certified engineers in your directory. When you're dealing with really technical noise control engineering, I definitely recommend taking a look at this directory. And finally, in review, sound absorption is classified by the noise reduction coefficient, or NRC rating. NRC is specifically related to the behavior of sound within a space, echo and reverberation, sound reflections. Sound transmission class, STC, this is specifically related to airborne sound transmission through a wall. And then impact insulation class, this is related to the footfall noise that you hear in the floor ceiling assembly above you. All right, and with that, Adam will be joining us and we'll read off any questions that we have.
All right, thanks a bunch, Eric. Yeah, we've had several questions come in. Thanks everybody for hanging with us and submitting your questions. We'll get to as many as we can with the time we have left today. If we don't get to your question, we can follow up via email with answers to that. But first off, so going back to some of the questions we had earlier in the presentation, there's a question that came up in reference to the ASTM E90 testing and wanted to know, can the overall size of the tested opening affect the overall STC result? Meaning, like, will the result in a higher or lower STC value?
Yeah, very good question. So theoretically or mathematically, the STC rating is weighted for the area of the sample. So theoretically, the answer is no, that regardless of the size of the sample, you should get the same STC rating. However, there are real differences in real life related to the way the sample will vibrate or resonate if it's larger or smaller. ASTM E90 for wall assemblies requests a minimum size of 2.4 meters by 2.4 meters, so basically 8 feet by 8 feet. And then this is considered to be large enough where those kind of structural vibration issues are not contributing to that result. For items that are smaller than this, it's allowed in the standard to test them at their actual size. So for example, a 3x7 door, you can test at 3x7. Now, I agree it would be completely unreasonable to ask a door manufacturer to test at 3 foot, at 36 by 84, at 37 by 85, at 38 by, it's unreasonable, and nobody has that kind of data. So you have these sort of unofficial standard sizes that have developed in doors and windows. And then on the window side of things, I think like NFRC or some of the air, water, structural, thermal testing that fenestration or window manufacturers are required to do dictate standard sizes, and those have kind of become unofficial standard sizes in the world of sound testing as well. So that's a long way around of yes and no, and it kind of depends on the circumstance. We pretty much refuse, and some of the people on the call may have experienced this, we'll refuse to do things that heavily impact the performance in a way that kind of makes things unfair comparison. That's really the philosophical purpose of this testing, is to have comparison of different products. So we really try to steer things towards those more or less standard sizes.
Okay, the next question that we have is, why is the reference curve for IIC test shaped the way it is shaped? Is it delivered from a common FC assembly construction?
Yeah, that's a good question. And it's also similar to the STC curve shape, right? So I actually don't know the answer to that. So generally, humans are more sensitive to higher frequency sounds. And that's why I think that's why both the STC and IIC curves are more punishing towards high frequency sound and more forgiving towards low frequency sound. Assemblies also tend to pass more readily lower frequency sounds and are generally more effective to high frequency sounds. So the curve has that sort of approximately mass law type of curve to it, or profile to it. So that's my guess, but I don't actually know the true answer to that. So.
Okay, next question around STC rating, asking about for the STC rating in aluminum framing with glass, is there anything to add into the frame to help achieve a higher rating?
That's a good question. The reason I'm pausing is it's important as a lab to have a certain level of confidentiality for your customers, and what we have seen, how we have seen some customers perform differently than others. We don't sell that information to other customers, and we don't basically give away their techniques. What I will say is that I do believe that the way the glass is held does affect the way the glass will resonate and the way the glass will pass sound to a certain degree. Now with the frame, you know, sometimes things that perform better for thermal will also perform better for acoustics, where you have a break in the structure. But yeah, at the end of the day, I actually don't have expertise really in the design of fenestration systems as much as I do on the ability to test them. So I do have customers that that probably know that answer, but I don't. So.
Okay, question that's referring to earlier in the presentation, I believe for slide 11, wondering approximately how does the absorption of a sample standing vertically differ than the same size sample laying down? Is it something that's close to double?
Okay, so there are two different ways I can interpret your question, and I'll try to answer it both ways. So first, you'll notice that most of our testing is performed on the floor of the chamber. We call it the test surface. It's and because gravity does not have a big influence on the way sound flows and reverberates through the chamber, the floor of the chamber could represent the wall or the ceiling. It does not matter. So the fact that the sample is on the floor versus the wall, that is totally irrelevant and does not affect the performance. And for practical reasons, it's easier for us to install material on the floor because gravity helps keep it in place, basically. So if material was installed on the floor of the chamber, flat with no airspace, versus on the wall of the chamber, flat with no airspace, assuming all else is equal, there would be no difference in performance. But I think what you might be asking, or alternatively, you might be asking if that same wall panel, rather than being flat on the floor directly, was tested upright or vertically, how would that affect the performance? Well, in terms of Sabins, or total square feet of sound absorption produced, you're going to see a reduction in sound absorption at low frequencies and a boost in absorption at high frequencies. Why? Because you kind of effectively made that material thinner by removing the benefit of the reflected path through it, if that makes sense. And some of the benefit of having the material against the boundary of the chamber. At low frequencies, those would be beneficial to be flat to the wall or chamber floor. But at high frequencies, you've exposed more surface area to the sound field. So sound waves will see more area that's absorptive. We call it type K mounting, which is the common mounting type for office screens. We would use the ASTM C423 allows you to calculate coefficients for K mounting, which is the office screen, but you must use the area of both sides. So that's why you often see office screen partitions have, you know, what you think might, you know, you have a 2-inch thick office screen that's all sound absorption material. You think that should get a 1.0, but you may see something like a 0.75 or 0.85, depending on what it is. So it's part of it is because both faces are used in that calculation and the various reasons I discussed before about how that changes the performance.
All right, let's get 2 more questions in here, and then we'll get everybody out for the day. So next question here we have, are air gaps as effective as material thickness, or does the air gap simply aid in achieving a better result that cannot just be achieved by the material alone?
That's a really good question. So I think at some frequencies, I think it's frequency dependent. In the upper end of the spectrum, it's gonna be similar, but I think at lower frequencies, you would be better off at having 2 inches of solid sound absorption media than you would 1 inch plus a 1 inch airspace. So I think that is, a consideration, but that airspace really makes a big difference. So you think of it as airspace is free. All it costs you is floor area. So, but yeah, if you're really trying to hit the biggest number at lower frequencies, you'd be better off using more thickness of material. That's something, yeah, that's a good idea for a novelty test series. I like that. So maybe we'll test that and publish something on it.
All right, great. And last question that we have here, can the NRC value be over 1.0 based on reporting methods?
Yes, and it's not surprising or alarming. It's not a sign that something was done wrong. Early on, when we talked about NRC and sound absorption, and remember, NRC is an average sound absorption coefficient for frequency average, and sound absorption coefficients can exceed 1.0. And the reason is because that term is used incorrectly, because they are not actually energy absorption coefficients. They are units of sound absorption per unit area, so sabins per square foot. And it's possible to achieve greater than 1 sabin per square feet of material in the reverb chamber. A lot of reasons that contribute to that, but yeah, that was probably surprising when they started running these tests to Wallace and Paul Sabin. I think some of it is attributed to the boundary. They call it the edge effects, and I don't mean the exposed edge. That's often what people will think is like when I'm referring to exposed insulation on the edge. No, even if the edge is sealed, you'll still have edge effects. What it is that boundary between the sound absorption material and the reflective floor is fuzzy for the sound waves. It's not like a clean laser. It's not like a clean knife cut, and there's some excess absorption around the boundary. So I think it's true that if we had an infinitely large sample, and if we could still achieve diffuse field condition with that infinitely large sample, which is impossible, you would never exceed 1.0. So some of it is an artifact of the test, and I also think some of it's an artifact of the equation, but people are still researching that.
All right, I think that's all the time we have for the questions. Like I mentioned, if we didn't get to yours today, we'll take a look at these and follow up by email here in the coming days to you as well. So thanks,
and
everyone.
You see this email address on the screen. Always feel free to reach out. We're here to help.